Alright folks, we have some mind-blowing news to share. Brace yourselves because AdaTape, Google's latest AI tool, is causing quite a stir with its jaw-dropping 99.9% success rate. That's right, you heard it correctly, this bad boy is smashing records left and right. Alright, let us break down what AdaTape is for you. It's this amazing AI tool created by the brilliant minds at Google, and let us tell you, it's crazy accurate. In their paper titled Adaptive Communication with Elastic Input Sequence, Google introduces a fresh model that makes use of adaptive computation. This model is built on a transformer-based architecture and uses a dynamic set of tokens to create flexible input sequences. It brings a whole new level of adaptability when compared to past works. Trust us, it's pretty cool. So AdaTape is this cool new model, uses adaptive computation in a really clever way. If you're not familiar with adaptive computation, it basically means that a machine learning system can adjust its behavior depending on the situation. Unlike traditional neural networks that have a fixed function and capacity, adaptive computation allows the model to allocate computational resources based on the complexity of the input. This means that the model can work harder on difficult tasks and take it easy on easier one. It's like having a machine learning tool that knows when to put in more effort and when to take it easy. Adaptive computation is all about changing how a machine learning system operates based on what it's dealing with. Pretty neat, right? When it comes to neural networks, they can be all adaptable and stuff by using different functions or computation budgets for different inputs. It's like a deep neural network is this function that gives you a result based on both the input and its parameters. And get this, to make it even more adaptive, certain parameters are activated based on the input. They call it conditional computation. Alright, let's talk about AdaTape and what it brings to the table. Imagine a transformer-based architecture that uses a dynamic set of tokens to create elastic input sequences. This approach offers a fresh perspective on adaptability when compared to previous models. Think of AdaTape as a tape reader machine that can read data from a tape and perform calculations. It has the ability to adjust itself and understand various tokens added to the input, regardless of their complexity. In contrast, other adaptive models use dynamic depth to allocate computation budget by adjusting the number of layers or iterations used for each input. However, this approach can introduce instability and complexity during both training and inference stages. So with AdaTape, we have a more flexible solution that addresses these challenges. Overall, AdaTape brings exciting possibilities for enhancing adaptability in transformer architectures. Its unique features make it an intriguing option worth exploring further. So basically, AdaTape is an AI tool that uses adaptive function types and a dynamic computation budget. It takes a batch of input sequences, tokenizes them, and then uses a vector to select a sequence of tape tokens from its tape bank. This tape bank stores all the candidate tape tokens that interacts with the model through an adaptive tape reading mechanism. There are two methods for creating the tape bank, an input-driven bank and a learnable bank. So basically, the input-driven bank is all about extracting a bunch of tokens from the input. It's different from the original model tokenizer because it maps the raw input to a sequence of input tokens in a unique way. This allows for dynamic and on-demand access to information from the input, but with a fresh perspective. Think of it as an embedding layer that the model can use to retrieve tokens based on how complex the example is. The learnable bank gives AdaTape a super flexible tape bank, so it can adjust its computation budget depending on how complicated each input is. It picks a bunch of different tokens from the tape bank for each sample. The cool thing is that the tape bank can be controlled by input, like getting some super detailed info or using a set of vectors that you can train. Basically, adaptive tape reading selects different sequences of tokens from the tape. They can be different lengths depending on the input. Then these tokens are just tacked onto the inputs and sent to the transformer encoder. Easy peasy. Okay, AdaTape really knows how to handle some tough stuff. They were given this challenging task to study how inductive biases affect performance. And guess what? AdaTape totally crushed it. It outperformed all the other methods by adding a little recurrence into its input selection. This gave it a cool advantage and allowed it to maintain a counter that the others couldn't do. The standard transformer and universal transformer, yeah, they couldn't even come close. Their performance was like random guessing, which is pretty lame, but not AdaTape. They were on another level. So yeah, that's pretty cool, right? So AdaTape is actually super interesting when it comes to evaluating image classification. It was trained on ImageNet 1K from scratch and it performs way better than the alternative adaptive transformer baselines in terms of quality and cost trade-off. And get this, larger AdaTape models are even faster than smaller baselines. They totally outperform other methods like AVIT and Universal Transformer VIT, with an impressive top 1 accuracy of 83.8% using only 86 parameters and 84.5 flops. That's some serious performances out there. AdaTape is awesome at tackling tasks like addition, multiplication, and sorting. It's incredibly accurate and doesn't require a lot of computing power compared to other models on the market. Plus, it offers a great balance between quality and cost. You can either achieve higher accuracy at a lower cost or find the perfect trade-off that suits your need. Unlike other models that use complicated algorithms, AdaTape keeps things simple with a fixed number of layers. This ensures stability and prevents memory and speed issues. It's also much easier to work with compared to complex models like a mixture of expert models, which can be tricky to handle and parameterize properly. With AdaTape, all parameters are used equally, so you don't have to worry about any problems or complications. Determining whether a binary string has an even or odd number of bits may seem like a simple task to some, but it poses a challenge for conventional transformers. Unlike regular transformers that treat long and short strings equally, AdaTape adapts its methodology based on the length of the string. It allocates more resources to longer strings and fewer resources to shorter ones, resulting in greater efficiency and accuracy, especially for longer strings. In fact, AdaTape achieves an impressive accuracy rate of 99.9% on tasks involving 256-bit binary strings. While standard transformers lag behind at just 50.1%, this significant disparity demonstrates the remarkable capabilities of AdaTape in this field. So let's take a look at how efficient AdaTape is. It's actually a really practical tool that can greatly improve accuracy when needed. What sets it apart from other adaptive baselines is its incredible efficiency, thanks to its unique approach of incorporating adaptivity directly into the input sequence rather than the model depth. We can measure this efficiency using two methods, flops per sample and latency per sample. Flops per sample calculates the number of floating point operations required to process one input sample, while model latency per sample measures the time it takes to process one input sample. When compared to other adaptive models across various tasks and benchmarks, AdaTape consistently achieves lower flops per sample and latency per sample. But check out the impressive results of ImageNet 1K. With the addition of tape, it achieves 4.5 flops per sample and a latency of 3.2 milliseconds per sample, all while maintaining an 83.8% top 1 accuracy. In comparison, other tools only achieve 7 flops per sample and a 4 millisecond latency with 82% top 1 accuracy. AdaTape can totally achieve a top 1 accuracy of 4.2% with only 5.5 flops per sample and a super quick latency of 3.8 milliseconds per sample just by adding more tape token. But wait, there's more. AdaTape can also achieve a top 1 accuracy of 2.4% with only 3.5 B flops per sample and an even faster latency of 2.6 milliseconds per sample by decreasing the number of tape tokens. How cool is that? So yeah, tapes are pretty awesome. The heat maps actually show that AdaTape tends to go for the patches in the center more often. Makes sense though, because those central patches are usually packed with information, especially in datasets with natural images where the main object is usually right smack in the middle. It just goes to show how smart AdaTape is, being able to identify and prioritize those high-value patches to boost its performance. So here's the deal with AdaTape. It's all about that adaptive tape reading mechanism that gives it elastic sequence lengths, and that brings a whole new level of flexibility to the table. It opens up possibilities for solving tasks that even standard transformers and other adaptive architectures struggle with. We put AdaTape through some serious testing on image recognition benchmarks, and guess what? It blew standard transformers and adaptive architecture transformers out of the water while working with the same amount of computing power. Pretty impressive stuff. When this thing hits the market, it's gonna be a game changer for everyone. So keep an eye out for Google's AdaTape because it's gonna revolutionize the way we create and consume everything. The possibilities are endless, but the possibility of you subscribing to our channel is possible. And also, don't forget to leave your thoughts on this AI tool on your way.